Hi everyone, welcome to goclasses. In this lecture, we will discuss cache memory, ISRO previous year questions, UGC NET PYQs and GATE PYQs. Cache memory is very important from GATE exam point of view. Every year, at least two questions come from cache memory. I can say 3 to 4 marks every year come from cache memory in the GATE exam. Okay, so let's discuss all the questions from ISRO, UGC NET, GATE PYQs. Let's do the complete analysis of all the questions. Let's solve this question from UGC NET. Which of the following mapping is not used for mapping process in cache memory? Associative mapping, direct mapping, set associative mapping, and segmented page mapping. So, which of the following mapping is not used? The answer will be option D, that is segmented page mapping. This is not used. The remaining associative mapping, direct mapping, and set associative mapping, these are used as mapping techniques in the cache memory. Remember, we have already seen cache memory mapping techniques. There are three mapping techniques for cache memory. We have direct mapping, we have fully associative mapping, and set associative mapping. Remember, what is cache mapping technique? What is a cache mapping? Basically, the cache mapping techniques, they give the answer to the following question. Which question? The question about where should we put the main memory block in the cache memory. When we fetch from main memory, when we fetch a block, a memory block, when we fetch to the cache memory, then where should we put it? Okay, this is the question. And the answer of this question is given by the mapping techniques. We can either use direct mapping or fully associative mapping or set associative mapping. So you can see this is the question. When we copy a block of data from main memory to the cache memory, then where exactly should we put it? This is the question. To answer this question, we have these three mapping techniques. You can use any of them. Now remember, depending on which mapping technique you use for your cache memory, the cache memory we can classify into three types. So you can see there are three types of cache memory. We have direct mapped cache, it will use direct mapping. We have set associative cache, it will use set associative mapping. And we have fully associative cache. When the cache memory uses fully associative mapping, then we call it fully associative cache. So remember, depending on which mapping is used, which mapping technique is used by the cache memory, we can classify the caches, we can divide the cache memories into three types. These are the three types of cache memories, and these are the three types of mapping techniques. Very simple. Now let me just revise what are the three type of cache memories. We have direct mapped cache, set associative cache, and fully associative cache. Let me tell you what is a direct mapped cache, or I can say what is a direct mapping. In direct mapped cache, remember, every main memory block maps to a unique line. So you can see every main memory block that will map to a unique line. In the set associative cache, every main memory block will map to a unique set. In the set associative cache, every set has multiple lines. For example, this is two-way set associative cache, means every set has two lines. So you can see in the set associative cache, every main memory block maps to a unique set. In the direct mapped cache, every main memory block will map to a unique line. And in the fully associative cache, any main memory block can map to any line. Very simple. Okay. So these are the three type of cache memories. Very simple. So for this question, the answer will be which of the following mapping techniques is not used as mapping technique in the cache memory. The answer is option D, segmented page mapping. This is not used as a mapping technique in the cache memories. Very simple. With every question, we will also revise the related concept, then we will solve the questions. Okay. Let's solve UGC NET June 2005 question. The principle of locality of reference justifies the use of virtual memory, interrupts, cache memory, secondary memory. The principle of locality of reference justifies the use of, the answer is cache memory. Let's understand why. First, what is this principle of locality? You can see what is this principle of locality of reference. Let's understand this. So all these concepts we have seen in our cache memory lectures, but let's do the revision. So you can see what is principle of locality, or I can say locality principle, or I can say locality of reference. It is very simple. Most of the programs, they have locality property. What is locality property? In most of the programs, what happens that the location, the memory location that CPU accesses in the near future, either CPU will again access that same memory location, or it will access the nearby memory locations. So it happens in majority of the programs. I can say that majority of the programs have this locality property. Remember, this property is called locality. You can see. So what is this locality property? Very simple. In simple words, when the program will access a memory location, then in the near future, either the program will again access that same location or it will access the nearby locations. Okay, this is called locality property. So you can read this, that most of the programs, majority of the programs, they tend to use data or instructions with addresses near or equal to those they have used recently. So very simple, this locality property basically says that most of the programs, what they do, they access data and instructions with addresses near or equal to those they have accessed recently. Okay, means as a program, if I'm accessing some memory location, then it is likely that in the near future, either I will access that same memory location again, or I will access the nearby memory locations. Okay, this is called locality property, and this locality property most of the programs exhibit. Means most of the programs, they have this locality property. Now let me tell you, there are two type of locality property. One is temporal locality, another is spatial locality. So let's see the definition of temporal locality and spatial locality. Temporal locality, what it says that when a program accesses a memory location, then in the near future, it is likely, there is a good chance that the program will again access that same memory location. This is called temporal locality. So you can see the principle of temporal locality says that if a program accesses one memory address, then there is a good chance that in the near future it will access the same address again. You can see this is the diagram. From this diagram you can understand the temporal locality. The temporal locality means if the program accesses a memory location, this is the memory location. If a program accesses this memory location, then there is a good chance, it is very likely that in the near future the program will again access the same memory location again. So this is called temporal locality property. Another is spatial locality property. Spatial locality says that if the program accesses a memory location, then there is a good chance, it is very likely that in the near future, the program will access the nearby locations, the nearby memory location. Very simple. So this is called spatial locality. The principle of spatial locality says that if a program accesses one memory address, like this memory address, then there is a good chance, it is very likely that in the near future, the program will access nearby locations. Okay, very simple, you can see nearby addresses. So these are the two type of locality property, temporal locality and spatial locality. And there is a good news that most of the programs, majority of the programs, they have both these properties, temporal locality and spatial locality. Okay, so you can see the definition of temporal locality, spatial locality here also. Temporal locality simply means that recently referenced items, means recently accessed items are likely to be referenced again in the near future. What is spatial locality? It says that items with the nearby addresses are likely to be referenced in the near future. Okay, so these are called temporal locality and spatial locality. Now you might be thinking, what does this locality principle has to do with cache memory? Why we discuss the locality principle, temporal locality, spatial locality, when we discuss the cache memory? Very simple. The cache memory takes advantage of temporal locality. How the cache memory will take advantage of temporal locality? It is very simple. Initially, let's assume cache memory is empty. Okay, initially there is nothing in the cache memory. We already know that cache memory is logically divided into lines, and the line size is equal to block size. Okay, so this is the cache memory, and this is the CPU. Correct. Now let's assume initially the cache memory is empty, and this CPU wants to access this memory location. Okay, you can see. So this CPU, let's assume this generates the memory address. This CPU will generate the memory address, let's assume that is 1100. So CPU wants to access this memory location which contains the data n. Okay, and this is the memory address, that is 1100. Okay, and remember, in our computer system we have memory hierarchy. So remember, the CPU will always generate the main memory address. So CPU has generated this main memory address 1100, but because there is a memory hierarchy in our computer systems, so first we will go to the cache memory. We will check in the cache memory if this address is available or not. This cache memory is empty, so I can say there is a cache miss, because this address is not available in the cache memory, so there is a miss. When there is a miss, then this cache memory will send the request to the main memory. So now you can see from the main memory we will access the main memory, and from the main memory we will access this address. Okay, and now how this cache memory will take the advantage of temporal locality? I told you that majority of the programs they have this temporal locality, means if they access some address, like if the program is accessing this address 1100, then it is very likely, there is a good chance that in the near future very soon the program will again access this same memory address. Yes or no? So now we assume that we already know that the majority of the programs they have this temporal locality property. This we already know. Okay, now of course if majority of the programs have this temporal locality property, then we will assume that our program also has a very good chance that our program also has this temporal locality property, right? Now you can see if our program accesses this memory address 1100, then we know that in the near future very soon our program has a good chance of accessing this same address again. So what we do, instead of again in the future again instead of going to the main memory to access this address, what we can do, we can put this address in the cache memory. Basically we can put this data in the cache memory. So what we can do, from the main memory we will bring this data to the cache memory and we will put it here. Okay, so that by the temporal locality property, in the near future very soon if the program again accesses this same memory address, then the next time we don't have to go to the main memory. Next time we can find this memory address in the cache memory and there will be cache hit. So the CPU can access this data, this memory address from the cache memory, and it will take less time because cache memory access time is very low and the main memory access time is very high. So this is how the cache memory will take the advantage of temporal locality. Very simple. So if someone asks you how the cache memory takes advantage of temporal locality, your answer will be what? Your answer will be that cache memory takes advantage of temporal locality by copying the data from main memory to the cache memory, so that next time in the future very soon if the program accesses this same address again, then we will next time we will get the data in the cache memory and we will not have to go to the main memory. So by copying the data from main memory to the cache memory, the cache memory will take the advantage of temporal locality. And remember one more thing, this cache memory will only copy the active data in the cache memory, right? Active data means the data that's program, or I can say CPU wants currently. Yes or no? Active data means what is the data that CPU wants at this moment. Okay, or I can say in the nearby moments. So you can see that is called active data. So what we do, when CPU wants to access some address, then we put that address, we put that data in the cache memory to take the advantage of temporal locality, so that in the near future if CPU accesses that same address again, then we will find it in the cache memory. Very simple. Okay, so this is how the cache memory will take the advantage of temporal locality. And remember, cache memory also takes the advantage of spatial locality. How? Because I told you the property, this spatial locality property, this property says that if CPU wants to access some memory address, if CPU accesses some memory address, then it is very likely, there is a good chance that in the near future very soon the CPU will access the nearby addresses, right? Okay, so remember, for example, just for example sake, let's assume that CPU wants to access this address 0010. Okay, let's assume CPU wants to access this memory address 0010. Okay, CPU generated this main memory address 0010. Okay, now initially let's assume that the cache memory is empty, so there is nothing in the cache memory. Now this CPU wants to access this address 0010, but we know that most of the programs have spatial locality. Okay, so we will copy this data, remember, because CPU wants to access this address 0010 and this is not available in the cache memory, so there is a cache miss. So of course this data we will copy from main memory to the cache memory. But remember, we know that there is a spatial locality property in most of the programs. So spatial locality says that if CPU accesses this memory address, then in the near future very soon the CPU will access the nearby addresses. Now if we already know that very soon in the near future CPU will access the nearby addresses, then what we can do, instead of copying only this data in the cache memory, what we can do, we can put nearby data also, means we can fetch a block of data from main memory to the cache memory. Okay, so remember, this block of data we can fetch from main memory to the cache memory, and this block, let's call it block 0. and this block 0 we can put in the cache memory. Now, by putting this block in the cache memory, by fetching a block of data from main memory to the cache memory, the cache is taking the advantage of spatial locality, because by the definition of spatial locality, by the spatial locality property, if CPU is accessing this 0010 address right now, then very soon in the near future CPU will access the nearby addresses. Now you can see, if in the near future very soon CPU accesses the nearby addresses, then it is very likely that CPU will find this in the cache memory, because we are fetching a block of data from main memory to cache memory. So by fetching a block of data from main memory to the cache memory is taking the advantage of spatial locality. Okay, very soon, very simple. I hope you understood this point. So remember, if we increase the block size, then what it means? Increasing the block size means, if I make the block size is equal to 8 bytes, then what it means? It means that we are taking more advantage of spatial locality. Is this clear? If the program has more spatial locality, then increasing the block size means we are taking more advantage of spatial locality. But the point is, from main memory to the cache memory, we transfer a block of data, and the reason is very simple, because we want to take the advantage of spatial locality, and majority of the programs have spatial locality. So fetching a block of data from main memory to the cache memory will benefit us. Okay, very simple point. So you can easily see, if someone asks you why we do block transfer from main memory to cache memory, the reason is very simple, because we want to take the advantage of spatial locality. And one more thing, why we put the active data in the cache memory, the reason is very simple, because we want to take the advantage of temporal locality. So cache memory will take the advantage of temporal locality, also cache memory will take the advantage of spatial locality. Okay, we have already seen. So you can see this meme. Cache memory is thinking that most of the programs, majority of the programs have this locality property, so benefit kar sakte hain, we can benefit. Okay, so this is the meme you can see. So let me conclude that the effectiveness of cache memory in our systems, in the modern computer systems, we use this cache memory. Also, we use this memory hierarchy in the modern computer systems. And let me tell you why they are effective, why this cache memory is effective, why this memory hierarchy is effective. The effectiveness of cache memory and the effectiveness of memory hierarchy is due to the property of locality of reference, and this property is shown by most of the programs. Okay, so remember, because most of the programs have this locality of reference property, temporal locality and spatial locality, that is the reason cache memory is effective. That is the reason memory hierarchy is effective. If majority of the programs don't have this temporal locality, spatial locality, or I can say locality property, then remember, this cache memory concept will not be effective, and also this memory hierarchy concept will not be effective. Because of locality property, these two concepts are effective, and that is the reason we use these concepts in the modern computer systems. Very simple point. So for this UGC NET exam question, the principle of locality of reference justifies the use of cache memory and memory hierarchy. So for this question, let me tell you, the answer will be that property of locality of reference. Majority of the programs have this locality property, and that is the reason cache memory is effective, and that is the reason this memory hierarchy is effective. So you can see, this locality property justifies the use of cache memory, and memory hierarchy. If they ask you some MSQ question, and in the MSQ question this cache memory option is also there, and this memory hierarchy option is also there, then remember, the answer will be both cache memory and memory hierarchy. These are successful. These two concepts are successful only because of locality property, because of this principle of locality of reference. Very simple. Let's solve GATE CSE 2001 question. More than one word is put in cache block to exploit the temporal locality, exploit the spatial locality, reduce the miss penalty, none of the above. What is the meaning of exploit? Let me tell you. Exploit means take advantage of. When you exploit someone, it means you are taking advantage of them. Okay, so first of all, let me tell you that what this word exploit means. So this exploit word, this simply means take advantage of. Take advantage of. Okay, so now let's solve this question. The question is saying that more than one word, or I can say more than one byte, is put in one cache block to take advantage of temporal locality of reference of the program, to take advantage of spatial locality of the program, to reduce the miss penalty, what is the answer? The answer will be option B. Means we put more than one byte, or I can say more than one word in cache block, in one cache block, to take advantage of special locality property of the program. Okay, remember what is spatial locality? We have seen in the previous question, the complete discussion we have done. We have seen what is spatial locality, what is temporal locality, how the cache memory will take the advantage of spatial locality, how the cache memory will take the advantage of temporal locality. All these concepts we have just now in the previous question we have seen. Okay, so but let me just focus on the spatial locality. You know what is the spatial locality? The definition of spatial locality is very simple, that spatial locality property says that if a program accesses a memory location, let's assume program accesses this memory location, then spatial locality property says that it is likely, or I can say there is a good chance that in the near future, very soon, the program will access the nearby addresses. So this is the definition of spatial locality. Spatial locality means if the program accesses a memory address, then there is a good chance that in the near future, very soon, the program will access other nearby addresses. You can see from this diagram, this is the diagram for spatial locality. To understand the spatial locality, if I access this memory address, then there is a good chance that in the near future, very soon, I will access the nearby addresses. This is called spatial locality property. Okay, and remember, the cache memory will take the advantage of spatial locality property by fetching a block of data from main memory to the cache memory. When there is a cache miss, then the cache memory will fetch a block of data from main memory, not only a single byte, but actually a block of data the cache memory will fetch from main memory to take the advantage of spatial locality. Okay, so you can see the cache memory will take the advantage of spatial locality. What is the reason? The reason is very simple. Let's assume CPU generates, let's assume CPU wants to access this memory address 0010. So remember, CPU is only interested in this memory address, but we already know that majority of the programs, they have this spatial locality property. So we know that if the CPU is accessing this memory address right now, then very soon in the near future, CPU will access the nearby addresses. This is the locality, this is the spatial locality property. Okay, and majority of the programs, remember, majority of the programs have this spatial locality property. So what we do to take the advantage of this spatial locality property, what we do, from the main memory, we fetch a block of data to the cache memory. Okay, this is our cache memory. So remember, the CPU wants to access this memory address 0010. So CPU is only interested in this memory address, but we know that there is a spatial locality property in majority of the programs. So to take the advantage of this spatial locality property, what we do, instead of fetching only this data to the cache memory, what we do, we fetch a block of data to the cache memory. So this block of data, let's call it block 0. This block of data we transfer to the cache memory. Okay, so let's assume the cache memory is a fully associative cache memory. So any block we can put in any line. Okay, this is not a direct mapped cache, remember. If it is a direct mapped cache, then this block we will put in this line. Okay, because in a direct mapped cache, any memory block will map to a unique line. Okay, so you can see, let's assume this is a direct mapped cache. Then you can see this CPU is interested only in this data C at this address 0010. But we know that to take the advantage of spatial locality property, we will fetch this block of data from main memory to cache memory. So this block of data we will put in the cache memory, because we know that right now this CPU is accessing this memory address, and by the spatial locality property, very soon the CPU will access the nearby addresses. So if we fetch this block of data to the cache memory, then in the near future, very soon, if CPU accesses the nearby addresses, for example this address, or I can say this address, then the CPU will find this address in the cache memory, so there will be cache hit. So this is called taking advantage of spatial locality property. Okay, very simple. So you can see, if someone asks you why we do block transfer from main memory to cache memory, the reason is very simple, because we do block transfer to take the advantage of spatial locality. Okay, remember, if the block size is bigger, then we are taking more advantage of spatial locality. So if you want to take more advantage of spatial locality property, then you will increase the block size. If your block size is very small, for example, if your block size is only 2 byte, 4 byte, then you are taking less advantage of spatial locality property. And if your block size is just one word, or I can say 1 byte, then basically you are not taking advantage of spatial locality property. Okay, if someone asks you that assume my block size is equal to 1 byte, or I can say one word, then we are not taking any advantage of special locality property. In a block we put multiple words, or I can say multiple bytes, so that we can take the advantage of special locality property, because we know that if CPU is accessing some memory address right now, then very soon in the near future CPU will access the nearby addresses. Okay, that is the reason when there is a cache miss, then we don't just fetch that requested data, we fetch a block of data, we also fetch the nearby data from main memory to the cache memory. This is called taking advantage of special locality property. Very simple. So you can see, for this gate exam question the answer will be more than one word we put in the cache block to take advantage of special locality property. Exploit means take advantage of. The cache memory wants to take advantage of special locality property. That is the reason the cache memory will fetch a block of data from main memory to the cache memory whenever there is a cache miss. Very simple. Okay, and let's see this option A. How the cache memory will take the advantage of temporal locality? Can you tell me? Just now we have seen in the previous question. Okay, so you can watch, you can see the explanation of the previous question to understand how the cache memory will take the advantage of temporal locality property. The answer is very simple. The cache memory will take the advantage of temporal locality property by copying the active data from main memory to the cache memory. Okay, very simple. Whenever the CPU wants to access some data, and if that data is not available in the cache memory, then we will fetch that data from main memory to the cache memory. This is called taking advantage of temporal locality. And whenever CPU wants to access some data and that is not available in the cache memory, then we fetch that data. Along with that data, we fetch a block of data to the cache memory from main memory. A block of data we fetch to the cache memory. This is called taking advantage of special locality property. So remember, the cache memory will take the advantage of temporal locality as well as spatial locality. Okay, let's see option C. This is saying that we put more than one word in a block to reduce the miss penalty. Do you think if we increase the block size, what do you think? The miss penalty will increase or decrease? What is your opinion? What is your analysis? Tell me. If we increase the block size, then this miss penalty, I'm asking, this miss penalty will reduce or it will increase? Let me know. It will increase, yes or no? If you increase the block size, then the miss penalty will increase. What is the reason? What is miss penalty? Miss penalty means once there is a cache miss, you have detected that there is a cache miss. Let's assume CPU wants to access some data. This is CPU, this is the cache memory, and this is the main memory. Okay, now what is miss penalty? Can you tell me? Miss penalty means, you know that CPU will generate some memory address. First, we will search in the cache memory whether there is a hit or a miss. If there is a miss, means the data is not available in the cache memory. Now, after the detection of the miss, we need to access the main memory. This is called miss penalty. Means after the detection of a miss, we have already detected that there is a miss. We have searched in the cache memory and we found that there is a miss. Now remember, after that, after the detection of a cache miss, the whole time taken, that is called miss penalty. Okay, and remember one thing, if I increase the block size, then what will happen? After the detection of a miss, you already know that from the main memory we will fetch a block of data to the cache memory, yes or no? So if the block size is more, then this will take more time. Do you agree with me? Because remember, after the detection of a cache miss, we are fetching a block of data. This block we are fetching from main memory to the cache memory. This block we are fetching, okay, this is the block, and we transfer this block from main memory to the cache memory. So you just tell me, it is a very common sense that if this block size is more, then this will take more time, this transfer will take more time. And if this block size is less, then this transfer will take less time. So very simple point, if the block size is very small, then this miss penalty will be less. If the block size is bigger, then miss penalty will be more. Okay, yes or no? So this is a very simple idea. So I can say that we put more than one word in the cache block to reduce the miss penalty. No, actually it will increase the miss penalty. Okay, yes or no? So very simple point, the answer will not be option C. And one more thing, instead of reduce the miss penalty, actually the block size, if you increase the block size, then miss penalty will increase. Okay, so you can see this here. If you increase the block size, then the miss penalty will increase, because The miss penalty, the name itself is telling you miss penalty means after the detection of a miss, what is the penalty that you will pay? And what is the penalty? The penalty is that we will fetch a block of data from main memory to the cache memory. Okay, one block of data we will fetch. So you can see if the block size is more, then this transfer from main memory to the cache memory will take more time. And if the block size is less, then this transfer from main memory to cache memory will take less time. So you can see this penalty that you will pay after the detection of a miss, this will be less if the block size is less. Okay, and if the block size is more, if you increase the block size, then the miss penalty will also increase. Very simple point. But remember, if you increase the block size, then miss rate will decrease. Okay, understand one thing, if you increase the block size, then miss penalty will increase, but actually miss rate will decrease. Why miss rate will decrease? Because if you increase the block size, let's assume there is a miss in the cache memory. Now let's assume there is a the block size is very huge, or I can say let's assume block size is 32 bytes. This is the block size. Now you can see if there is a miss right now, only there is one miss. Yes or no? Let's assume there is a miss. Now after one miss, what we do? We fetch this block from main memory to the cache memory. We are fetching this block. Now you can see if this block size is more, then this transfer will take more time. Basically miss penalty will be more. But there is an advantage also. What is that? The advantage is that because you are fetching a block and the block size is more, because this block size is more, you can see. So when we fetch this block to the cache memory, now next time if CPU accesses these nearby locations, then there will be hit. Yes or no? Is this point clear? So remember, if the block size is more, then when there is a cache miss, then we will fetch a block from main memory to the cache memory. If the block size is more, then basically we are fetching huge amount of data from main memory to the cache memory. So next time, by special locality property, majority of the programs they have special locality property. So by the special locality property, next time when the CPU will access these nearby addresses, and there is a good chance, the special locality property says that there is a good chance, it is very likely that CPU will access the nearby addresses. So next time when the CPU will access the nearby addresses, then CPU will find them in the cache memory. So I can say number of miss will decrease. Yes or no? If you increase the block size, then number of miss will decrease, but the miss penalty will increase. Miss penalty means if there is a miss after the detection of a miss, the whole time taken that will increase. If you increase the block size, then this transfer time from main memory to the cache memory that will increase. Okay, so I hope this point is clear. So remember, this is the relationship between block size, miss penalty, and miss rate. So if you increase the block size, miss penalty will increase. But remember, if you increase the block size, then miss rate will decrease, means number of misses will decrease. Okay, very simple point. So if you want to reduce the miss rate, then you can increase the block size. Means means in a single go you can fetch a large amount of data from main memory to the cache memory. This is the meaning of larger block size, because every moment when there is a cache miss, then we will fetch block of data from main memory to the cache memory. So if this block size is more, then you are fetching a large amount of data to the cache memory. Okay, and in the future there will be less number of miss. So you can see, reducing miss rate, to reduce the miss rate you can increase the block size, you can also increase the cache size, the cache capacity you can increase, or you can increase the associativity. You can see, if you go from direct mapped cache to fully associative cache, then basically you are reducing the miss rate, because in the fully associative cache, any main memory block you can put in any line. Yes or no? But in the direct mapped cache, there is a restriction that any main memory block you can put in a unique line. So if you increase the associativity, if you go from direct mapped cache to fully associative cache, then basically you are reducing the miss rate. Okay, so this is the complete idea, and this is the complete explanation, complete analysis of this question. So remember, in this gate exam question, the block size, we put more than one word in a block to take advantage of special locality property, and it will not reduce the miss penalty, it will actually increase the miss penalty. Okay, very simple. Let's solve NIELIT 2017 question. In a cache memory, if total number of set is s, then the set offset is, means how many bits we need for set offset. Actually they should ask you that what is the number of bits required for set offset. This should be the question. Don't worry, in the NIELIT exam the questions are not well framed. Many questions are very ill framed, or I can say very poorly framed. Okay, so don't worry. In this question they should ask you that if the total number of set is s, then what is the number of bits required for set offset. This is what they should ask you. Okay, but anyway, let's see this. We have total number of set equal to s. Then what is the number of bits required for set of set? That will be log s. Yes or no? Because remember, if you have 8 set, let's assume in your cache memory, let's assume there are total 8 set. Then set of set means what? If you have total 8 set, then to identify one of them, how many bits you need? In the cache memory, total you have 8 set. We have total 8 set. Then to identify one of them, how many bits we need? Only 3 bits we need. Yes or no? So you can see if the number of set is 8, then we need 3 bits. 3 bits required for set offset. Required for set offset means to identify one of these sets, we need 3 bits. Okay. So if you have total n number of sets, then what is the number of bits required for set offset? That will be log base 2 n. This will be the number of bits required. This will be the number of bits required for set offset. Okay, very simple point. So for this question, the answer will be option B. Let's solve ISRO 2020 question. How many total bits are required for a direct mapped cache with 128 KB of data and one word block size, assuming a 32-bit address and one word equal to 4 bytes? Let me tell you, this is a very poorly framed question. And that is the reason I am giving you a well framed question. I can say a well framed version of the same question. Again, I'm telling you, this ISRO 2020 question, this is a very poorly framed question. Okay. It has a lot of data missing. A lot of information is missing from this question. So this is a poorly framed question, very poorly framed question. And that is the reason, let me give you a well framed version of the same question. The same question I've converted into a well framed question. Okay, so you can see this is the well framed version. Now, what you need to do, you need to solve this well framed version only. Okay, so let's solve this well framed version. We have direct mapped cache with 128 KB of data. This is the size of data array. Remember, we already know that cache memory consists of data array and tag array. In the cache memory, there are two parts. One is data array, another is tag array. This tag array, this is also called tag directory. Now, in this data array, we put the data that we fetch from the main memory. Means the actual data, the actual blocks that we fetch from the main memory, we put them in the data array. So remember, in this data array, this is actually a line. Okay, you can see these are the lines. So you can see this is actually a line, and line size is equal to main memory block size. So you can see in this line here, you put the main memory block that we fetch from the main memory. So that block actually we put here, means here goes the block, the main memory block we put here. So in the data array, this data array is logically divided into lines. Line size is equal to block size. So you can see in this data array, we put the blocks that we fetch from the main memory. Very simple. And associated with every line, there is a tag. So you can see in the tag array, we store the tags. Also, we store the valid bit, dirty bit, all the status bits we store in the tag directory, or I can say tag array. But remember, associated with every line, you can see here, if you have 8 lines, then there are total 8 tags. You can see with every line, there is an associated tag. With every line, there is an associated tag. So in this tag array, we store the tags associated with all these lines. Very simple. Also, with every cache line, there is an associated valid bit, dirty bit, all these things. So those are also stored in the tag directory. One more thing, when we discuss the cache memory size, by default, it does not include the tag array size. Means when we say that cache memory size is something, then it simply means we are only talking about the size of data array. Very simple point. So you can see we have two parts in the cache memory. There is cache data array, there is cache tag array, or I can say tag directory. So you can see cache memory consists of data array and tag directory. And in this data array, what we put? In this data array, we put the actual data, means the main memory blocks that we fetch from the main memory, those we put in the data array. So this data array is logically divided into lines. And what about this tag array? This tag directory, this stores the meta information. The extra information is stored in the tag directory. And remember one thing, in the tag directory, the number of entries, that is same as number of lines, because associated with every line there is a tag. Okay, so you can see that the number of entries in the tag array, that is same as number of lines in the data array. And in this tag array, what we do, we store the tags associated with each cache line. Also we store the status bits like valid bit, dirty bit, LRU information, something like that. Okay, so all the extra information we put in the tag array. Very simple. Okay, by default, when we say that cache memory size is 32 KB, it means this is the data array size. This does not include the tag array size, or I can say tag directory size. Is this clear? Very simple. So let's solve this question. This is the ISRO question. This is a poorly framed question, and this is the well framed version of the same ISRO question. So let's solve this question. We have a direct mapped cache with 128 KB of data. So this is basically the data array size. Okay, the question has given us the data array size, and the data array size, that is 128 KB. 128 KB of data. You can read this question. We have a direct mapped cache with 128 KB of data. This is the data array size. In the cache memory, there are two parts: data array, tag array. So this is the data array size. You can see it's designed with 32-bit addresses. This is the address size. This is the main memory address size, because the CPU will generate the main memory address. So remember, this is the main memory address size. By default, main memory is byte addressable. So if you have 32-bit address size, then it means in the main memory there is 2 power 32 bytes. That is the main memory size. So if you want, I can also write here main memory size. What that will be? That will be 2 power 32 bytes. This is the main memory size. And what is the cache memory size? That is equal to data array size. So remember, 128 KB of data. This is basically cache memory size. Because I told you that by default, cache memory size does not include the tag array size. By default, when we say that cache memory size is 128 KB, it simply means we are talking about the data array size. Okay. Next, you can see the cache memory uses a block size of 4 bytes. So this is the block size given to us. Block size is equal to line size. So you can see block size is given to you, that is 4 bytes. And the main memory address size, that we already know, main memory address size, that is 32 bits. Next, the question says that every cache line, each cache line has valid bit, one valid bit, there is a tag field and data block. Okay, so basically every cache line has this valid bit, tag field and data block. Let me tell you, this valid bit and tag field, these are stored in the tag array. These are stored in tag array part. These are stored in tag array, and this data block, this is stored in the data array. Okay, this is stored in data array. So you can see now the question is asking what is the total size of cache memory including the tag array size, including the data array and tag array size. So remember, in this question they want to ask you the total cache memory size including the tag array and data array. If they do not mention this line, if they directly ask you what is the cache memory size, then remember that does not include the tag directory size. So if they directly ask you what is the cache memory size, then answer will be 128 KB. But they are asking you total cache memory size, which includes the tag array also. One more thing, if they ask you total cache memory size, but they do not mention this line, okay, then also remember total cache memory size is equal to data array size only. But in this question, they are explicitly saying that we want to include the tag array size also. Okay, so again, I'm telling you, if the question explicitly says, if the question writes that find the cache memory size including the tag directory size, then only you need to consider the tag directory size. Otherwise, if the question asks you what is the cache memory size or what is the total cache memory size, okay, if the question does not mention to, if the question does not explicitly say to include the tag directory size, then do not include the tag directory size in the cache memory size. Very simple point. Okay, I hope you understood. Now let's solve this question. So you can see this is the data that is given to us. Now we need to find what is the total cache memory size, including the tag directory and data array. Okay, so how to find that? First, we need to find what is the number of lines, because you know that number of lines that will be equal to the number of entries in the tag array. So you can see this is the data array that is divided into lines. So this is the data array. Okay, here you can notice what is this. This is the number of lines. This is the number of lines. Correct. Now you already know that associated with every line there is a tag tag stored. Okay, so I can say this is basically tag array. Okay, so let me make this diagram. This is the tag array, and we already know that associated with every cache line there is a tag stored. Okay, we stored this tag in the tag array. So you can see we store the tag also. Here we store the tag also, and here we store the valid bit. Yes or no? So remember this tag and valid bit, this is stored in the tag array, or I can say tag directory. Okay, so first we need to find what is the number of lines. Okay, so what will be the number of lines? That will be equal to the data array size, or I can say the cache memory size. This is the cache memory size. Okay, cache memory size divided by the line size. Line size is equal to block size, that is 4 bytes. So here you can see this is basically 2 power 17 divided by 2 power 2, that is 2 power 15. These many lines are there. Okay, so if you have these many lines, it means these many tags are stored, these many valid bits are stored. Okay, because associated with every line there is a tag stored, there is a valid bit stored. Okay, so you can see total we have how many valid bits? 2 power 15. So I can say here basically 2 power 15 entries are there. Very simple point. Okay, now what we need to calculate? We need to calculate what is the tag size. Yes or no? So let's find out the tag size. We have a direct mapped cache. In a direct mapped cache, what is the address division? How can we divide the physical address? In a direct mapped cache, we can divide the physical address into three parts: the tag field, the index field, and also the block offset. So you can see this is the address division. This is the memory address division, main memory address division. So the main memory address size, that is 32 bits. Okay, and that 32 bits we can divide into three fields. You can see tag, index, and block offset. In a direct mapped cache, this index means line index. This will tell you about the line number. So this index means line index. And remember, what about this block offset? Or I can say directly offset, block offset, or you can call it offset. If you call it offset, then also it means block offset. Okay, and if your main memory is byte addressable, then we can also call it byte offset. And remember, by default main memory is byte addressable, so you can also call it byte offset. If your main memory is word addressable, then you can call it word offset. Okay, so very simple. Now let's see what is the size of tag field, how many bits I need for tag. So very simple. First you find what is the block offset size, how many bits you need for block offset. The block size is 4 bytes. So what about the block offset size? How many bits we need for block offset? That will be 2 bits. Okay, because in one block you have 4 bytes. So to identify one of them, you need 2 bits. So very simple. Here you need 2 bits. What about index? Index means line index. In the direct mapped cache, index means line index. So what is the number of lines? That is 2 power 15. So this index needs 15 bits. Very simple. And you can see what about this tag? How many bits required for tag field? That will be total is 32. Okay, because the total address size, that is 32 bits, minus 15 for index, minus 2 for block offset. So this will become 15 bits. Yes or no? So I can say that for tag we need total 15 bits. Very simple. Now you can see that in this diagram, you can see that for this tag you need 15 bits. Here you need to store 15 bits. Very simple. Of course, for valid bit only 1 bit you need. So 1 bit you need here. Okay, and here what you will store? Here you will store the block. Yes or no? Here the memory block you will store. And what is the block size? That is equal to 4 bytes. So very simple point. You can notice that total we have 2 power 15 lines, and in one line what you need to store? In one line you need to store this block also 4 bytes, and associated with every line there is a tag stored and there is a valid bit stored in the tag directory. So this is the tag directory part, this is the data array part. Here I can say total we have 2 power 15 entries, and in one entry, what is the total size of one entry? That is 15 bits plus 1 bit, that is 16 bits plus 4 bytes. So you can see one entry size. Here I can say that one entry size, okay, including the tag, valid bit, and the block size. Okay, so I can say basically one entry total size, I can say 1 bit for valid, okay, plus 15 bit for tag, and plus 4 byte. So remember, this is bit, okay, this is also bits, and this is 4 bytes. Is this clear? This 1 bit, this is for valid bit, valid bit, okay, and you can see this 15 bits, this is for tag stored, and this is for block, or I can say the data, actual data. Okay, so total you tell me what is the one entry size? The one entry size, that will be 4 bytes. That means what? 4 into 8, 1 byte equal to 8 bits. So that is basically 32 bits, right? Okay, yes or no? 32 bits. So I can say 32 plus 16, that will be 48 bits total. Okay, and if you divide by 8, then that will be basically 6 bytes. Okay, now I can say what is the total cache memory size, including the tag directory size and data array size, what that will be. So I can say the total cache size, including tag array and data array, that will be equal to 2 power 15 entries are there, means 2 power 15 lines are there, and what is the one entry size? That is 6 bytes. So that will be the final answer. So let's see the options. What are the options here? You can see the options are in the bits. Okay, so let's convert into bits. Is that clear? So this byte we can convert into bits. So basically 2 power 15 into 48 bits. Okay, because the options are given in bits. Now let's see what is this 2 power 15 into 14 bits. What that will be? Remember, all the options are given to you in megabits. Okay, you can see megabits, and 1 m, 1 mega, that is basically 2 power 20, right? So you can see here you have 2 power 15. Let's convert this into 2 power 20, then we can write it m, capital M means mega, because all the options are given to you in megabits. So what we can do here, this 2 power 15 into 48 bits, let's multiply with 2 power 5 and divide by 2 power 5. Okay, so you can see this 2 power 5, 2 power, this 2 power 15 into 48, let's multiply with 2 power 5, divide by 2 power 5. Now you can see this will become capital M, and what this will become 48 divided by 25, that is means 48 divided by 32, that will become 1.5. So you can see this will become 1.5, that will become capital M, and this is bits. So your final answer will be 1.5 capital M bits. This will be the final answer. So I can say this will be same as 1.5 megabits. Okay, and remember what is 1 M? That is equal to 2 power 20. 1 G, capital G, that is equal to 2 power 30. 1 K, that is equal to 2 power 10. Okay, so here you can see that your answer will be 1.5 megabits. So for this question, the answer will be option D. I hope you understood this question. So remember, this question is actually a well-framed version of this ISRO exam question. This ISRO exam question is a very poorly framed question. The complete information is not given in this question, but this question I have converted into a well-framed question, and then you can solve it, and your answer will be option D. That is 1.5 megabits. Very simple question. I hope you understood. Let's solve UGC NET 2020 question. Consider a machine with a byte addressable main memory of 2 power 16 bytes and block size 8 bytes. Assume there is a direct mapped cache consisting of 32 lines. How many bits will be there for tag line word field of main memory address? You already know that this in the direct mapped cache we can divide the main memory address into three fields, three parts: tag, index. Index means line index. Okay, in the direct mapped cache, index means line index, and in the set associative cache, index means set index. Okay, so you can see because it is a direct mapped cache, so the main memory address I can divide into three parts: tag, line index, and block offset. Okay, so this is what the question is asking, basically the number of bits required for tag, for index, and for block offset. So let's solve it. We already know that the physical address division in the direct mapped cache, in the direct mapped cache, the main memory address, or I can say the physical address, we can divide into three parts: tag, index, and offset. Here this index in the direct mapped cache, this index means line index. This index will tell you about the line number, and this offset means block offset. This offset means block offset. And remember, if your main memory is byte addressable, which is by default the main memory is byte addressable. So if your main memory is byte addressable, then I can also call it byte offset, because if the main memory is byte addressable, then at every address there will be a byte, you will find a byte. So I can say this offset, I can also call it byte offset if your main memory is byte addressable, which is the by default. Okay, by default in every question, by default main memory is byte addressable. But if the question says explicitly, if the question says that main memory is word addressable, then we need to consider the main memory to be word addressable. If the question does not explicitly say that main memory is word addressable, then always we need to consider that main memory is byte addressable. So that is the reason this offset, you can also call it byte offset, you can also call it block offset. Okay, very simple. And this is the tag and this is the line index, very simple. So let's solve this question. First we need to find what are the block offset size, how many bits we need for block offset. So you can see that block size, that is 8 bytes. If the block size is 8 bytes, then how many bits we need for block offset? That will be only 3 bits. Yes or no? 3 bits block offset, 3 bits offset. Very simple. And let's find what the number of bits required for index, means for line index. So you can see that number of lines, that is 32. So if number of lines is 32, then what is the number of bits required for line index? What is the number of bits required for index field? That will be 5 bits. Yes or no? 5 bits for line index, or I can say for index. Very simple. Now you know that the main memory has 2 power 16 bytes. Okay, and the main memory is byte addressable. This is also given to you, that the main memory is byte addressable, means at every address there is 1 byte. So you can see that the main memory size, that is 2 power 16 bytes. What it means, if the main memory size is 2 power 16 bytes, then the address size, that will be 16 bits. Yes or no? So here you know that main memory address size, from here you can calculate main memory address size, that will be equal to 16 bits. Okay, because in the main memory there are 2 power 16 bytes, and every byte has an address, because the main memory is byte addressable, so every byte has an address. So that is the reason, to address a byte we need how many bits? That is 16 bits. So the main memory address size, that is equal to 16 bits. Very simple. Now it is very simple question. So this is the physical address. Physical address means main memory address. So this is the main memory address. Okay, main memory address size, that is 16 bits. So this is basically 16 bits. Okay, and this address I can divide into three parts. In the direct mapped cache, we can divide the physical address into three parts. You can see this least significant part, this is the block offset. For that we need 3 bits. So this is the offset field. For that you need 3 bits. Next you have this index field, which is the line index, for which you need 5 bits. And this is the tag field. So for this tag field, how many bits you need? That will be equal to the total number of bits in the address, that is 16, minus the number of bits required for index, that is 5, minus the number of bits required for offset, that is 3. So this value will become 8 bits. So I can say for tag you need total 8 bits. So you can see number of bits required for tag, that is 8. The number of bits required for line, that is 5. And the number of bits required for word field, basically this means word offset, or I can say byte offset. I told you, if the main memory is byte addressable, Then block offset, you can also call it byte offset. Okay, so actually here they are saying word field, but actually they should say, either they should say block offset, or they should say byte offset, or I can say byte field. Okay, instead of saying word field, they should say byte field, or I can say byte offset or block offset. These words they should use here. Okay, but anyway, this is also fine. We understood what they want to say. They want to say block offset. So you can see for block offset you need 3 bits. So finally the answer will be option A, that is 853. Very simple question. Let's solve ISRO CSE 2017 question. A cache memory needs an access time of 30 nanosecond. This is the cache memory access time. Main memory access time, that is 150 nanosecond. What is the average access time of CPU? From CPU point of view, what is the average access time if the cache memory hit ratio, that is 80%? This is a very simple question. We have a single level of cache memory. There is only one level of cache memory, and then there is a main memory. So remember, we have a memory hierarchy in our computer systems. So when the CPU will generate the main memory address, CPU will always generate the main memory address. Now when the CPU generates the main memory address, then first we will go to the cache memory. We will search in the cache memory whether there is a hit or a miss. If there is a hit, then we will not access the main memory. If there is a hit in the cache memory, then main memory is not involved. Okay, so I can say if the data is available in the cache memory, then we only need to access the cache memory, that's it. But if the data is not available in the cache memory, then what? Then also remember, because there is a memory hierarchy in our computer system, so when the CPU will generate the address, but the data is not available in the cache memory, then also after CPU generates the address, first we will go to the cache memory. We will search in the cache memory whether there is a hit or a miss. Now we will find that okay, there is a miss. After that, CPU will say this cache memory. The cache memory will transfer the request to the main memory, and then we need to access the main memory. So very simple point. Whether there is a hit or whether there is a miss, in every situation we need to access the cache memory to check whether there is a hit or a miss. If there is a hit, then we will only access the cache memory. We will not access the main memory. But if there is a miss, then we will also access the main memory. That is called miss penalty. Means after you detect the miss in the cache memory, after that you need to access the main memory. So that is called miss penalty. Means this is the additional time required when there is a miss in the cache memory. So miss penalty means the additional time required when there is a cache miss. So that is called miss penalty. Okay, so here you can see we need to find what is the average memory access time from the CPU point of view. What is the average access time? So the formula we already know, that average memory access time, that is equal to hit time, cache hit time plus miss rate into miss penalty. And remember, we have a single level of cache memory, so this miss penalty, that is equal to main memory access time. Okay, all these concepts we have seen in our lectures, in our average memory access time lectures. You can watch all the average memory access time lectures, you can watch on the YouTube. So on YouTube you can search goclasses AM80, goclasses average memory access time. This you can search on the YouTube. You will find this average memory access time part 1, average memory access time part 2. These two lectures you can watch if you want to learn, if you want to understand the correct concept. Okay, so let's see. You can see I told you that if there is a single level of cache memory, then this miss penalty, this is same as main memory access time. So here you can see this miss penalty, this will be same as main memory access time when there is a single level of cache memory. So you can see this miss penalty is equal to main memory access time when we have single level of cache. Okay, so very simple point. So here I can say this miss penalty, this is equal to main memory access time. What is this hit time? This cache hit time, this is same as cache memory access time. Okay, and this miss rate, this is the cache memory miss rate, and this is same as 1 minus hit rate. Okay, so that's it. Now you can just apply this formula and you can get your answer. So what will be the average memory access time? So here I can say average memory access time, or I can say AM80, that is equal to cache memory access time, that is equal to 30 nanosecond plus what is the miss rate? If the hit rate is 80%, then the miss rate is 20%. If you convert into fraction, it will be 0.20. You can divide by 100. So you can see the miss rate is 20%. If you convert into fraction, then you will divide by 100. So you will get 0.20, or I can say 0.2. Multiply with miss penalty. What is miss penalty? When you have a single level of cache memory, then miss penalty is same as main memory access time. So that will be 150 nanosecond. All the data that is given to you in nanosecond, so you don't have to worry about the unit. Okay, very simple. So options are also given to you in the nanosecond. So you can calculate this value and that will be the answer. So that will be 30 plus what this will become. This will become 30, right? So the answer will be 60 nanosecond. So the answer will be 60 nanosecond for this question. The answer will be option A. Remember, this formula is actually very intuitive. This hit time plus miss rate into miss penalty. This formula is very intuitive. Why? Because for every access, there are two situations. Either the data will be available in the cache memory or the data will not be available in the cache memory. In every situation, whether there is a cache hit, whether there is a cache miss, in every situation, we need to access the cache memory because we have a cache hierarchy. So when the CPU will generate the main memory address, then first we will go to the cache memory. We will search in the cache memory whether there is a hit or a miss. So you can see whether there is a hit, whether there is a miss, whether the data is available in the cache memory or the data is not available in the cache memory. In every situation, we need to access the cache memory. So you can see that is the reason this cache memory access time plus. Now, when do we pay the miss penalty, or I can say when do we pay the extra time? When do we spend the extra time? That will happen only when data is not available in the cache memory. So when the data is not available in the cache memory means miss rate. So this miss rate multiplied by miss penalty. Miss penalty means this is the additional time required for access when the data is not available in the cache memory. And when there is a single level of cache memory, then this miss penalty is same as main memory access time, because if the data is not available in the cache memory, then after the cache miss detection, we need to access the main memory. That is the reason this miss penalty is equal to main memory access time if you have a single level of cache memory. All these concepts we have seen in these lectures, you can watch on YouTube. One more thing, there are many misconceptions in the average memory access time concept. For example, the misconception of simultaneous access or parallel access. This is a misconception, let me tell you. Also, the misconception related to look aside cache. All these misconceptions I have discussed in these AMAT lectures. Okay, so you can see, was the AMAT lectures, average memory access time lectures, on the goclasses YouTube channel, to understand what are the misconceptions, to understand what are the correct concepts, correct definitions, correct formula, correct derivation, correct proof, and a lot of standard questions, gate PYQs, everything. So you can see in these two lectures, you will learn all the correct concepts, you will get to know all the misconceptions, you will learn all the correct definitions. Also, you will solve a lot of standard questions and gate PYQs. So these two lectures you can watch. You can search on goclasses. You can search on YouTube goclasses AMAT. This is what you can search on YouTube. Okay. The link I will provide you in the description and in the pinned comment also, so you can check it out. Let's solve ISRO December 2017 question. A two-way set associative cache with capacity 16 KB and the block size is 8 words. The word length is 32 bits. The physical address space is 4 GB. The number of bits in the tag and set field. So this is a very simple question. We have a set associative cache memory. In a set associative cache memory, the physical address we can divide into 3 parts: tag, index, and block offset. And in the set associative cache, index means set index. Yes or no? So let's solve this question. First, let's find what is the block offset size, or I can say number of bits required for block offset. You can see what are the block size here. The block size is 8 words. This is the block size, that is 8 words. Now, one more thing, I have seen many students, when they see the block size is 8 words, then immediately they assume that main memory is word addressable. But that is wrong. Is it given in the question? Is it explicitly given that main memory is word addressable? Tell me. Is it explicitly written that main memory is word addressable? Is it explicitly written in this question? No, it is not written. Yes or no? So by default, main memory is always taken to be byte addressable. Okay. We will take main memory to be word addressable only if and only if it is explicitly written in the question that main memory is word addressable. You can see in this question, it is not written that main memory is word addressable. So by default, main memory is always byte addressable. Here also you need to consider that main memory is byte addressable. So all the data that you have in words, you can convert into bytes. You can see word size that is equal to 32 bits means 4 bytes. Okay, so you can see this is the word size given to you, that is equal to 4 bytes. So what you can do, all the data that is given to you in words, for example, this block size, this is 8 words, you can convert into bytes. So I can say it will be basically 8 into 4 bytes. So that will be 32 bytes. Okay. So if the block size is 32 bytes, then tell me what will be the block offset size? If the block size is 32 bytes, then the block offset size that will be only 5 bits, because 32 means 2 power 5 bytes. Yes or no? So here you can see this is the 32 bytes, means this is basically 2 power 5 bytes. Okay. So this block offset size, the number of bits required for block offset, that will be equal to 5 bits. And we have a set associative cache. So we need to find what is the number of bits required for index. Index means set index. In the set associative cache, we already know that index means set index. Index is same as set index. Okay. So what you do, you find the number of set in this cache memory. So let's find what is the number of set in this cache memory. So first we will find what is the number of lines. So to find the number of lines, what we can do, we can divide the cache memory size with line size. Line size is equal to block size. So what is the cache memory size? That is 16 KB. This is the cache memory size 16 KB divided by line size, that is block size. Block size is 2 power 5 bytes, or I can say 32 bytes. So here you can see it will be 2 power 9 lines. Okay, because here you have 2 power 14 divided by 2 power 5, that is 2 power 9 lines. So these many lines we have in the cache memory, but we need to find what is the number of set. So the number of set, that will be equal to the number of lines divided by, in one set how many lines we have? We have two-way set associative cache, means in one set we have two lines. Okay, so number of lines divided by the associativity. The associativity is equal to 2, because in one set we have two lines. So the number of set, that will be equal to 2 power 8. If the number of set is equal to 2 power 8, then what is the number of bits required for index, or I can say set index? So I can say that index field needs 8 bits. Okay, very simple. And we already know that in the set associative cache memory, we can divide the physical address into three parts. These parts are tag, index. In the set associative cache, index means set index, and there is a block offset. Okay, so you can see this block offset needs how many bits? We have already found that is 5 bits. So block offset needs 5 bits. And this index means set index, this needs 8 bits. So what is the number of bits required for tag? You can see the address size. From here you can find what is the address size. So you can see that main memory address, that is main memory size is 4 GB. You can see physical address space, that is 4 GB. This is the main memory size. So if the main memory size is 4 GB, this is main memory size, and that is equal to 4 GB. 4 GB means 2 power 32 bytes. Okay, so if the main memory size is 2 power 32 bytes, then, and because our main memory is byte addressable, by default the main memory is byte addressable, so what will be the address size? That will be equal to 32 bits. Okay, is this clear? So here I can say that physical address size, or I can say main memory address size, that will be equal to 32 bits. Okay, very simple. So you can see that this total we have 32 bits. So what is the size of tag field? How many bits we need for tag field? That will be equal to 32 minus 8 minus 5, and that will be equal to, I think, 19. Correct? 19 bits. That's it. So our answer will be the number of bits in tag and set field. What that will be? In the tag field we need 19 bits, and in the set field we need 8 bits. So for this question the answer will be option B. Very simple question. Let's solve NIELIT 2017 question. In a particular system, it is observed that the cache memory performance gets improved as a result of increasing the block size of the cache memory. What is the primary reason behind this? This is a beautiful question. The question says that in a particular system, in a particular computer system, it is observed that when you increase the block size, then cache memory performance is also improved. Then what is the primary reason behind this? That you are increasing the block size, and also with that the cache performance is getting improved. Then what is the primary reason behind that? That is the spatial locality. It simply means that the program that you are running in your system, that program has a lot of spatial locality. Remember what is spatial locality? Spatial locality means if the program or if the CPU is accessing some memory location, let's assume CPU want to access this memory location, then the spatial locality property says that in the near future, very soon, the CPU or the program will access the nearby addresses. Okay. So this is the spatial locality property, that if the CPU is accessing some memory location, then in the near future, very soon, it is likely, there is a very good chance that the CPU will access the nearby addresses also. Okay. So that is the reason what we do. Because of this spatial locality property, we fetch a block of memory, or I can say we fetch a block from main memory to the cache memory. Whenever there is a cache miss, then we fetch a block of data from main memory to the cache memory to take the advantage of spatial locality, because we already know that right now CPU is accessing this memory address, but by the spatial locality property, the CPU will access the nearby addresses in the near future. Okay, so that is the reason whenever there is a cache miss, we fetch a block of data from main memory to the cache memory. The reason is spatial locality. And if you increase the block size, then we will take more advantage of spatial locality. If you decrease the block size, then we will take less advantage of spatial locality. Now, if you are increasing the block size, let's assume this is the block size. Now, if you increase the block size, and then if the performance is getting better, it simply means the program that you are running, that has a lot of spatial locality, because increasing the block size means we are taking more advantage of spatial locality. Decreasing the block size means we are taking less advantage of spatial locality. If our program that I'm running, if that program has more spatial locality, means that program has a property, that program want to access the nearby addresses. Whenever it will access some address, then it will also access the nearby addresses. This is the property that that program has. So if our program has a lot of spatial locality, then increasing the block size will improve the performance, because we will be taking more advantage of that spatial locality. But remember, if your program that you are running, if that program does not have spatial locality or has very less spatial locality, then increasing the block size may not give you better performance. Okay, so basically increasing the block size will give you better performance if there is a there is more spatial locality in the program. And in most of the programs, there is good amount of spatial locality. In majority of the programs, in most of the programs that we run, there is a good amount of temporal locality, there is a good amount of spatial locality. These two property majority of the programs, almost all the programs have. So this is a beautiful question, that we are increasing the block size, and then we observe that cache performance is also getting improved. Then the primary reason is that the program that we are running, that has a lot of spatial locality, and that's why when you increase the block size, then you are taking more advantage of that spatial locality, and that's why the performance is getting improved. Okay, so the answer for this question will be that the program that we are running, that has a lot of spatial locality, programs exhibit spatial locality. So for this question, the answer will be option D. Let's see option A. Programs exhibit temporal locality. See, this has nothing to do with the block size. Okay, so this temporal locality has nothing to do with the size of block. Very simple. Okay, next, the programs have smaller working set. No. The read operation is frequently required rather than write operation. No. The reason is very simple. If you are increasing the block size and performance is also getting improved, it simply means that the program that you are running, that has a good amount of spatial locality, that has a lot of spatial locality. That's why increasing the block size means we are taking more advantage of spatial locality, and that's why the performance is getting improved. So for this question, the answer will be option D. Let's solve NIELIT 2020 question. A direct mapped cache of size 32 KB has block size 32 bytes. CPU generates 32-bit address. The number of bits for indexing the cache. Remember, in a direct mapped cache, index means line index. We already know that in a direct mapped cache, this address, this main memory address, this physical address, remember, we can divide into three parts. The three parts are tag, index, and offset. Offset means block offset. And what about index? In a direct mapped cache, index means line index. In a set associative cache, index means set index. So in a direct mapped cache, index means line index. Okay. Now let's see. So we need to find what are the number of lines. Then we can easily find the number of bits required for index field. The number of bits required for indexing the cache. So for that, we need to find the number of lines. How to find the number of lines? Number of lines that will be equal to cache memory size 32 KB divided by the line size. Line size is equal to block size, that is 32 bytes. So you can see number of lines that is equal to 2 power 10. These many lines we have in the cache memory. So if you have these many lines, 2 power 10 lines in the cache memory, then for index field, we need 10 bits, because in the direct mapped cache, index means line index. So if you have 2 power 10 lines, then for index field, we need total 10 bits. Okay, so here you can see number of bits required for indexing the cache. The answer will be option C. Let's solve this question. A computer system uses 16-bit memory address. This is the memory address size, that is 16 bits. It has 16 KB cache memory. Okay, this is the cache memory size, or I can say this is the cache data array size. Because in the cache memory, there are two parts, data array and tag array, or I can say tag directory. By default, when we say cache size, it means we are only considering the data array size. Remember, when we say cache memory size is something, then we do not include the tag array size, or I can say tag directory size. Okay, so this 16 KB cache, this means this is the data array size, cache data array size, that is 16 KB, organized in four-way set associative manner. So we have four-way set associative cache, 64 bytes per cache block. So this is the block size, that is 64 bytes. Assume that size of each memory word is 2 byte. This is the word size. This statement has no relevance to this question. The reason is very simple, because if you read this question, the question does not say that main memory is word addressable. Okay, if the question does not explicitly say that main memory is word addressable, then by default we will always assume that main memory is byte addressable. So this word size, this has no relevance to this question. So this statement that assume that word size is 2 byte, this has no relevance to this question. When a program is executed, the processor reads data sequentially from the following byte addresses. Okay, all these addresses that are given to us, these are byte addresses. These are not block addresses. These are not block numbers. These are byte addresses, or I can say these are the main memory addresses, because our main memory is byte addressable, and this is written here that these are the byte addresses. These are the byte addresses. It simply means that our main memory is byte addressable. At every address you will find a byte. That is the reason the CPU will generate the main memory address, and because at every address you are getting a byte, at every address you will find a byte, because our main memory is byte addressable. So we can also say that main memory address is also called byte address. Okay, if your main memory is word addressable, then I can say that main memory address is word address. But by default, main memory is byte addressable. So I can say main memory address is same as byte address, because at every address you will get 1 byte. Very simple. Or I can say every byte has an address. Very simple. So the processor is generating these byte addresses. These are the main memory addresses that processor is generating. These are not the block numbers. You can see all the above addresses are in decimal values. So these are the decimal values of main memory addresses. And remember, these are not the block addresses. This is very important, because many students, they will consider these as block addresses. Okay, assume that cache is initially empty. The number of addresses that will hit in the cache, this is what we need to find. So in this type of situation, first we need to find what are the block numbers. This is important. Okay, so from these byte addresses, first you find what are the block numbers, means this byte address belongs to which block, this address belongs to which block, this main memory address belongs to which block, and this address, this main memory address, or I can say this byte address belongs to which block. So from this sequence of byte addresses, or I can say from this sequence of main memory addresses, always you find what is the sequence of block numbers. Okay. In this question, you can notice the replacement policy is not given. We have set associative cache, four-way set associative cache. So actually, they should give the replacement policy, but they did not mention what is the replacement policy. The block replacement policy is not given in this question. So I think that we will not need the block replacement policy when we solve this question. Okay, that is the reason this information is not given, because to solve this question, when we solve this question, then we will not need, there will be no need of block replacement policy. Okay, I think that is the reason the block replacement policy is not given in this question. Okay, from these main memory addresses, or I can say from these byte addresses, first let's find what are the block numbers, to which block these addresses belong. Okay, and remember the block size is given to you, that is 64 bytes. So you can see that block size, that is 64 bytes. So from the main memory address, from the byte address, how can we find the block numbers? Let's see. You can see this is the main memory. Let's zoom. This is our main memory. And in the main memory, the question is saying that the block size is 64 bytes. Means in one block, there are 64 bytes. You can see these are the bytes, like this is the byte 0, this is the byte 1, and so on. This is the byte 63. Okay, remember these are the bytes. I am saying these are the byte numbers. Okay, let me write here that these are the byte numbers. Okay, so let me write that these are the bytes. Okay, you can see these are the bytes, or I can say these are the main memory addresses, because remember every byte has an address. In the byte addressable memory, every byte has an address. This is the 0th byte, this has an address, this has address 0000 and so on. Okay, this has address 000 and so on. Last may at last MSB will be born. So you can see that these are the bytes. Okay, every byte has an address, this byte has an address, this byte has an address. Okay, and the question is saying that block size is 64 bytes. So you can see from 0 to 63, this is block 0. Yes or no? Okay, so you can see this is our block 0. This is the block 0, block 0, because the block size is given to you. Block size equal to 64 bytes. So the first 64 bytes, these are block 0. And remember, byte number that will start from 0. The address will always start from all 0. You can see the address of this byte 0, that is equal to all 0. Okay, and in this question, you can see the main memory address size, that is 16 bits. So actually in the main memory total we have 2 power 16 bytes. Okay, and the block size is 64 bytes. So the first 64 bytes, that will be our block 0. Okay, means this byte number 0 to byte number 63, they belong to block number 0. Very simple. Okay, now let's see the next one. You can see that byte number 64, you can see this is the byte number 64, right? Okay, okay, so you can see this is the byte number 64. From byte number 64 to byte number 127. Okay, yes or no? This will be our block number 1, because the block size is 64 bytes. So in every block there are 64 bytes. So you can see that this byte number 0 to 63, they belong to block number 0. Byte number 64 to 127, they will belong to block number 1. Yes, correct. Okay, let's see further. You can see this byte number 128, this is the byte number 128. Byte number 128 to byte number 191. Okay, yes or no? They will belong to block number 2. Okay, and so on. You are getting the idea, right? Okay, very simple point. So this is the main memory picture that I've shown to you. I've divided the bytes into blocks. You can see because the block size is 64 bytes. So the initial 64 bytes will belong to block 0. Then the next 64 bytes will belong to block 1. Then the next 64 bytes will belong to block 2, and so on. Okay. Now just tell me a simple point. If I ask you to which block the byte number 70 will belong to. Okay. For example, if I ask you byte address, okay, byte number, if I give you in decimal, let's assume the byte number is 70. Okay. And I am asking you that this byte number 70, this will belong to which block? Okay. From this byte number 70, can you tell me the block number? You already know from this picture, you can see that the block number will be 1, because byte number 64 to byte number 127, they belong to block number 1. Yes or no? So this byte number 70, this is in the decimal. Okay, because the byte numbers in this question also, the byte numbers are given to you in decimal. The byte addresses are given to you in decimal. And byte address simply means main memory address. Okay, byte address, I can also say that this is basically main memory address, and these are given to you in decimal. Okay, so you tell me, if the byte number is 70, means byte address is 70 in decimal. Okay, then to which block it belongs to, that will be block number 1. But can we write a formula here? Yes, we can write a formula. You can see that because block size is 64 bytes, so basically we need to divide this main memory into 64 bytes. 64 bytes, yes or no? Chunks of 64 bytes. Okay, the main memory we need to divide into blocks of 64 bytes. Okay, so to find the block number to which this byte number will belong to, what we need to do, we need to divide this byte number 70 with 64. Okay, should we take seal or should I take floor? What should I take? You can see this value will be 1 point something something something. Should I take floor or should I take seal? I should take floor. What is the reason? The reason is very simple, because the block number will start from 0. Notice block number is not starting from 1. The first block is block number 0. The second block is block number 1. The third block is block number 2. So please understand that block number is starting from 0. That is the reason I need to take floor. Okay. So you can easily see I need to take floor. And if I take floor, then I will get 1. And that is the correct answer. The block number is 1. I hope you understood this point. Okay, let me explain with few more examples. Let me give you the byte number. Let's assume byte number in the decimal. The byte address in the decimal. Either I can say byte number or I can say byte address in decimal. Let's assume that is 160. Okay, now you tell me to which block it will belong to. So from here, can you find the block number? Yes, very easily you can find the block number. To find the block number, this 160 you will divide by 64, because we are dividing the main memory into blocks of 64 bytes. Yes or no? So this byte address in the decimal, this you will divide by 64. Okay. Now this value will be 2 point something something something. Okay. Now what should I take? Seal or floor? I should take floor. What is the reason? Because the block number is starting from 0. Block number is not starting from 1. Block number is starting from 0. The first block is block number 0. The second block is block number 1. That is the reason I should take a floor. And from this photo, from this picture, you can easily understand that this byte number 160 will belong to block number 2. Okay, yes or no? In the block number 2, we have byte address 160. So that's the reason I'm saying, I'm just explaining that we will take this floor. Okay, so remember, if the byte number is given to you in the decimal, then to find the block number to which it will belong, what we need to do, we need to divide by 64 and then we need to take a floor. Okay, this is what we need to do. We need to take a floor. I hope you understood this point. So very simple. So this is the conclusion. Let me write it here. I hope you understood this point, that if the byte address is given to you, if the byte address in the decimal, if the byte address in the decimal is X, okay, then to find the block number in decimal, what we need to do, we need to do this, that this byte address, or I can say this byte number, divided by block size. Okay, and you take floor. Okay, yes or no? You take floor. This is the formula. Okay, you can remember this formula for future if you want, but it is very important that you understand it, because remember the block size is starting from 0, not from 1. The first block is block number 0, the second block is block number 1. So that is the reason we are taking here floor, this floor. Okay, so this is the conclusion. If you want to remember this formula, that is also fine, but you understand this formula, that if the byte address or the main memory address is given to you in decimal, that is x, then to find the block number to which this byte belongs, what we will do, we will divide this block number, we will divide this byte number by block size, and we will take a floor. That's it, very simple idea. So now from this sequence, let's find the block number sequence. Let's find block number sequence. Okay, very simple, that from this sequence we are finding the block number sequence. Okay, from here we are going to here. This is what we are doing, going from here to here. Okay, so what we need to do, as I told you, to find the block number from the byte number, these are the byte addresses in decimal, or I can say these are the byte numbers to which block they will belong to. We need to divide them by 64 and take floor. That's it, very simple. Okay, so you can see that, for example, this 128. So what will be the block number? Block number will be equal to 128 divided by 64 and take a floor. Okay, so you can see this will be equal to 2. The floor of 2, that also will be equal to 2. So actually we will get block number 2. Okay, so this is the block number 2. What about 144? This will also belong to block number 2. Okay, you can see for this 144, what will be the block number? Equal to 144 divided by 64, and you take a floor here. Okay, so you can easily see this value will be equal to 2. Okay, so that also belongs to block number 2. What about 2176? Let's divide 2176 with 2176. Let's divide this by 64. That is exact 34. Okay, so that's it, very simple. What about 2180? 2180 divide by 64, that is 34 point something. So you take a floor, that again will be 34. Okay, next 128, that we have already found, that is block number 2, that belongs to block number 2. And 2176, we have already found, that belongs to block number 34. Okay, is this clear? So you can see that initially the cache memory is initially empty. Now remember, when the CPU will generate this byte address, when the CPU will generate this main memory address, this is the main memory address. Remember, CPU will not generate the block number. CPU will generate the byte address, or I can say CPU will generate the main memory address. So when CPU generates this main memory address 128, then because initially the cache memory is empty, so there will be cache miss. So what we will do, from the main memory, we will fetch a block of data to the cache memory. So remember, CPU is interested only in this byte number 128. But from the main memory, we will fetch a block of data to the cache memory. And this 128, this belongs to block number 2. So from the main memory to the cache memory, we will fetch block number 2. So remember, for this, there will be miss. Okay, there is a miss for this address. When the CPU will generate this address, then there will be miss. But when the CPU generates this address, then there will be hit, because already this block number 2 is already in the cache memory. Okay, you can see when CPU generates this main memory address, then there will be miss, because initially the cache memory is empty. But from the main memory, we will fetch the complete block to which this address belongs. This address belongs to block number 2. So from the main memory, we will fetch the complete block number 2. Now the next time when the CPU accesses, when the CPU generates this address 144, then there will be cache hit, because this address belongs to block number 2, and the block number 2 is already present in the cache memory. So this will be hit. So I can say here, you can see it will be hit. Okay, remember, this is the benefit of converting this memory address sequence into block number sequence. this byte address sequence, or I can say this main memory address sequence, you can convert into block number sequence. Now you can see the benefit. You can see this is the miss, but then there is a hit. Okay. Next, you can see this is a miss. This block number 34, this is a miss. Then there will be hit here. Okay. And you can see this is already a hit. And you can see this is already a hit. Okay. So total how many hit are there? You can see total number of hit, that is 1, 2, 3, 4. Total 4 hit and 2 miss. So the question is asking how many hit are there. So the number of hit, that will be equal to 4. 4 hit are there. So for this question, the answer will be 4. I hope you understood this point. I hope you understood the explanation of this question. So remember, in any question, in any replacement based question, in any block replacement based question, if the main memory address sequence is given to you, if the byte address sequence is given to you, then you convert that into block number sequence. Okay. From the block number sequence, you can easily solve the question, because whenever there will be a cache miss, then whole block will be transferred from main memory to the cache memory. Okay. So remember, even though CPU is interested in only this address 128, but still, because we are fetching complete block from main memory to the cache memory, so the next time when CPU generates this address 144, then there is a hit. Okay. Because the block which contains this 144, that is already available in the cache memory. So that is the reason next time there is a hit. So you can see this is a miss. I can say this is a miss. This address is a hit. Okay. Very simple. I hope you understood the complete explanation. Let's solve this question. Consider a computer with 12-bit address space. So this is the main memory address space. Or I can say this is the main memory address size, that is 12-bit. Byte addressable main memory. At every address there is a byte, or I can say every byte has an address. It has data cache capable of holding 8 cache blocks. Means there are total 8 lines in the cache memory. Each cache block is 4 bytes. This is the block size. During a particular program execution, the processor issues memory read instructions to the following sequence of block addresses. These are the block addresses. These are not the main memory addresses. These are not the byte addresses. These are the block addresses. Okay. We have a two-way set associative cache that uses LRU replacement algorithm, least recently used replacement algorithm. And the cache memory is initially empty. The number of blocks that are hit in the cache for this program. So remember, in this question, we don't need to convert the given sequence into the block number sequence, because already we have sequence of block numbers. Already we have sequence of block addresses. So we just need to apply this LRU replacement algorithm, and that's it. Nothing else we need to do, because already this block number sequence is given to us. Now the question says that we have two-way set associative cache memory. So let's solve this question. You can see in the cache memory there are total 8 lines. Okay, so let me make the diagram of this cache memory. This is the cache memory. Okay, in this cache memory, total we have 8 lines. But the question says that we have two-way set associative cache. So every set has 2 lines. Okay, so I can say total we have 4 set. These are the 4 set. I can say this is the set 0, this is the set 1, this is the set 2, this is the set 3. And every set has 2 lines, because we have two-way set associative cache. Okay, so this is the photo of cache memory. That's it. This is the two-way set associative cache. These are the set numbers: set 0, set 1, set 2, and set 3. Remember, in a set associative cache memory, every main memory block, every memory block will map to unique set. But within the set, you can put the block into any line. Okay. One more thing, if you want to find to which set a memory block will map to, then how can we find that? Very simple. If main memory block number is given to you, let's assume main memory block number in the decimal. If it is given to you in the decimal, this main memory block number, let's assume that is equal to n. Okay, and you want to find to which set this main memory block will map to, because we already know in a set associative cache memory, every main memory block will map to unique set. Okay, so if you want to find to which set this main memory block number n, this will map to. So what you need to do, very easily you can find the set number. Okay, so to find the set number, what you will do, set number is equal to this block number in the decimal mode. What do, you divide this by number of set, and then you find the remainder. That will be the set number to which this main memory block will map to. Okay, so very simple point. And mode, this is mode means remainder operator, and mode number of set. So here I can say this will be n mod 4. Number of set is equal to 4. So this will give you the set number to which this block will map to. Okay, so what you do for all these blocks, first you find to which set they will map to. Okay, is this clear? So what you do in this question, first you find the set number sequence. Okay, means from this data that is given to us, from this data, what you do, you find the data of the set number sequence. Okay, means if I bring this block, this is the block number 128. If I bring this block from the main memory to the cache memory, then to which set it will map to. Okay, this is what we want to find. So as I told you, you divide the block number, the main memory block number, you divide by 4, and then you find the remainder. That will be the set to which that main memory block will map to. Okay, so here you can see from this main memory block numbers, from this sequence of main memory block numbers, you can find the set number sequence. So this 128, if I divide by 4, then I find the remainder, then what that will be? That will be 0. Okay, means this block number 128, this will map to set number 0. This will map to set number 1, because when you divide 129 by 4, then the remainder will be 1. When you divide 130 by 4, then the remainder will be 2. When you divide 131 by 4, then the remainder will be 3. Now, for the remaining block numbers, you just divide them by 4, and then you find the remainder. That will be the corresponding set number to which these blocks will map to. For example, this block number 189, this will map to set number 1. This block number 188, this will map to set number 0, because if I divide this block number 188 by 4, then the remainder will be 0. So this block number 188, this will belong to set number 0. So what you do, for all these block numbers, you divide them by 4, then you find the remainder, and then you find this set number sequence. Okay, so let me write it. So this is the sequence that we will get. This is the set number sequence corresponding to these main memory block number sequence. Okay, now let's solve this question. So here I have written the given main memory block number sequence. This is the given main memory block number sequence. You can see in this order. Okay, this is the given main memory block number sequence, and corresponding to that, what is the set number to which set they will map to, that also I have written here. Okay, now let's solve this question. The replacement algorithm, that is the LRU. Initially the cache memory is empty, so how many how many cache hit will be there, how many cache miss will be there, now we can easily find. So you can see that this 128 block number, this maps to set number 0. In the set number 0, I can put this block number 128 anywhere. So let me put this block number 128 here. Next, block number 129 will map to set number 1. Okay, so these are miss, right? Yes or no? This is a miss. So let me write it here. This is a miss. This is also a miss. Next, what about 130? Block number 130 will map to set number 2. Here I can put. Next, this is also a miss. 131 will map to set number 3. So 131 I will put here. Yes, this is a miss. What about 189? 189 will map to set number 1. Yes, there is a empty line available in the set number 1. So I can put 189 here. This is also a miss. Next, what about 188? This is the first time we are accessing block number 188. So this is a miss. This is a compulsory miss, because this is the first time, very first access of block number 188. Remember, the very first access of any main memory block is called compulsory miss. So this is basically compulsory miss. So far all these miss, basically these are the compulsory miss, because the very first access to any main memory block, that is called compulsory miss. So you can see this 188, this will map to set number 0. In the set number 0, there is an empty line available. So I can put this 188 here, no problem. Now let's see this 257. This will map to set number 1, but in the set number 1, all the lines are full. So we need to apply the replacement algorithm, LRU replacement algorithm. Basically, we need to replace one of these cache blocks with the main memory block, that is 257. Okay, so which of them we need to replace, that will be decided by the replacement algorithm, that is LRU list recently used. You can see this 129 and 189. This 189 is actually recently used, so this 129, this is the least recently used. So I will replace this and I will put 257 here. Yes, of course this is a miss, but it will replace the block number, the cache memory block number 129. Next, you can see the main memory block number 129 will be replaced by this main memory block number 257. Okay, now let's see the next, that is 256. Yes, this is a cache miss. This 256 will actually map to this main memory block number 256. This will map to set number 0. Set number 0 is already full, so we need to replace one of them with main memory block number 256. So LRU replacement algorithm we will apply, and this 128, because this is the least recently used, so I can replace this with 256. Okay, yes, this is a miss. Now what next? 128, is that a hit? No, that is a miss, because that is not available in the cache memory. So this 128 will map to set number 0. In the set number 0, the least recently used, that is 188. So I will put 128 here. Next 129, that is also a miss. That is also a miss. And I need to replace one of them in the set one of these 257 and 189. One of them I need to replace. So you can see that this 189, this is the least recently used. So here we can put 129. Okay, now let's see the next 131. 131, that is actually a hit. That is already available in the cache memory. So that is a hit. 189. 189 will go to set number 1. And yes, this is a miss. So we need to replace one of them, 257 or 129. So 257, this is the least recently used. So here we will put 189. What about 130? This will go to set number 2. Yes, this is a hit because it is already available in the cache memory. So this is a hit. 188. 188 is not in the cache memory, so this will be a miss. And we need to replace one of them, 256 or 128. So you can see 120, this 256 we will replace with 188. Anyway, you can see finally what is the number of hit. So the number of hit, that is only 2. Okay, all the remaining are miss. So for this question, the answer will be only 2, because the question is asking the number of blocks that are hit. So that will be 2. So for this question, the answer will be 2. Very simple question. I hope you understood. Let's solve GATE 2014 question. A 4-way set associative cache memory with capacity 16 KB is built using block size 8 words. The word length is 32 bits. The size of physical address space, that is 4 GB. The number of bits for the tag field, what that will be? This is a very simple question, but here let me tell you, many students, when they see this line, the word length is 32 bits. When they see this line in the question, then immediately they think that the main memory is word addressable. But that is wrong. Remember, we will consider the main memory to be word addressable only when it is explicitly written that main memory is word addressable. Here, is it written in this question? Is it explicitly given that main memory is word addressable? Is it given? No, it is not given. So by default, main memory is always byte addressable. So in this question also, you need to consider that main memory is byte addressable. Don't consider main memory to be word addressable unless it is explicitly written in the question that main memory is word addressable. Okay. So in this question, the data you need to convert into bytes. For example, the block size is 8 words. You need to convert this to bytes. Okay. So word size, that is 32 bits, means this word size, that is equal to 4 bytes. Okay. So from here, the block size, that is 8 words. So I can say that block size that is equal to 8 words I can convert into bytes. First of all, it is given to you 8 words. When I convert into byte, then this word means 4 byte. So it will be basically 8 into 4, that will be 32 bytes. So this is the block size. Okay. Next, you can see the size of physical address space, means this is the main memory size. The size of main memory is given to you, that is 4 GB. So I can say it is basically 2 power 32 bytes. This is the main memory size. And by default, main memory is byte addressable. So I can say that what is the number of bits required for address, for main memory address, for physical address, how many bits we require? That is 32 bits. Yes or no? So I can say that main memory address bits, main memory address size, that will be equal to 32 bits. The number of bits required for physical address, that is 32 bits. Very simple. Now remember, we have four-way set associative cache. In the set associative cache memory, the physical address is divided into three parts. Okay, these three parts are basically tag, index, and offset. Offset means block offset. Index, in the set associative cache, index means set index. Okay, so we need to find the number of set, so that we can also find the set index. Okay, means what is the number of bits required for index, or I can say set index, because in the set associative cache memory, index means set index. Okay, so let's find the number of lines first. In the cache memory, how many lines are there? Number of lines, that is equal to cache memory size divided by line size. Line size is equal to block size. So you can see block size is 32 bytes. So 32 bytes, this is the block size, or I can say line size. And the cache memory size, that is 16 KB. This is the cache memory size. So the number of lines, that will be equal to 2 power 9. These many lines will be there, because you can see it will be 2 here, and finally it will be 2 power 9. So you can see 2 power 9 lines are there in the cache memory. Now let's find what is the number of set. So the number of set will be equal to number of lines divided by associativity. You can see in one set there are 4 lines, because we have four-way set associative cache. So one set has 4 lines. Okay, so the number of set, that will be equal to 2 power 7. These many set are there. Now remember, because we have 2 power 7 set, so what is the number of bits required for index? Because in the set associative cache memory, index means set index. Okay, so you can see for index we need 7 bits. For set index we need 7 bits. Okay, next, now you can see that physical address we can divide into 3 parts. The 3 parts are basically tag, index, index means set index in the set associative cache, and the block offset. Block offset, or I can say offset, or I can say byte offset. So this is the block offset. Okay, now you tell me, for block offset how many bits we need? That we have found. You can see that block size is 32 bytes. So for block offset we need 5 bits. Okay, here I can say for block offset we need 5 bits. Okay, in one block there are 2 power 5 bytes. So for block offset, to address one of these bytes we need 5 bits. Okay, so you can see here we need 5 bits. For index, or I can say for set index, we need 7 bits. And what about tag? You can see the physical address size, that is 32 bits, minus 7 bits for index, minus 5 bits for block offset. So I can say here it will be 20 bits. Okay, this is the number of bits required for tag. Okay, so you can see the question is asking the number of bits for tag field, that will be equal to 20. So very simple question. For this question, answer will be 20. Okay, so that's it. We have seen all the UGC NET PYQs on cache memory. We have seen NIELIT exam PYQs on cache memory, ISRO exam PYQs on cache memory, and some GATE exam PYQs on cache memory. In this session, many questions, many previous year questions of multiple exams we have done. I hope you understood each and every question. I hope you understood the complete analysis of each and every question. We have done the complete analysis of every question. I hope you loved this session. Please share your feedback with me in the comments. Okay, please put a comment. Please like this session. Please put a comment and share your feedback with me. Okay, thank you everyone.